What is an irrational value? Despite how the name sounds, they aren't values that hold weird beliefs or refuse to listen to reasoning, although they can at first seem to defy logic. The name itself, irrational, means without a ratio. These are quantities that can't be described with fractions, or ratios of whole numbers. Since fractions can break apart values into tiny, even infinitesimally small bits, it might seem logical that fractions can describe any possible quantity. However, that isn't the case. For instance, let's take a square measuring 1 unit on each side and find the length of the diagonal. We could use the Pythagorean theorem and conclude that the diagonal has a length of the square root of 2. Using a calculator to find the square root of 2, it would spit back a decimal that starts 1.4142 and apparently goes on forever. It would be nice to find a simple ratio to describe how the diagonal compares to the width of our square. To do that, we would need to be able to describe both the width and diagonal of the square with whole number values. A fraction for the square root of 2 would be a whole number diagonal divided by a whole number width. A width of 1 obviously doesn't work, but we could scale up the square to different whole number widths and see if that makes a diagonal that would also have a whole number length. As the square grows, we can fit in more units along the diagonal, which helps the length sink in closer to a whole number value. But it's never an exact match. As opposed to continuing on blindly with this experiment, let's suppose for the sake of reasoning that we could eventually find a square that had both the width and the diagonal locked in on whole number values. Let's say that as we grow the square, this is the first one we would come to that does just that. So this square would make the smallest, simplest fraction for the square root of 2. Let's play with this further. We could fold the width up to meet the diagonal like this. This length could be described as diagonal minus width. Since we're working only with whole number values, diagonal minus width must also be a whole number. And this diagonal minus width edge can be folded over like this. And when we unfold it, we can see 3 edges with this same length. With these edges being the same, and a right angle here, we can extend it out to make a square. And this square's diagonal is width minus diagonal minus width, which is also a whole number. So what's significant about this smaller square? If, from our mental exercise, this square is the smallest possible one with whole number width and diagonal lengths, then we've just made an even smaller square that also has whole number values for its width and diagonal. In fact, we could keep repeating this process to make even smaller and smaller squares. A smallest square should exist, but it can't. We have an impossible paradox that the smallest square is never the smallest, which shows that we can't fit whole number units along both the width and diagonal of a square. This means that the square root of 2 is irrational and no fraction can describe it, no matter how big and complicated we try to make it. There can be a misunderstanding that just because irrational values appear in simple shapes like squares and circles, that somehow makes them elusive and impossible to measure. Irrational values may seem like nebulous ghost-like values, but they're just specific quantities that happen to defy being fully described with fractions.